Hey, what's up everybody, it's Ivan here, and over the last couple of weeks I was helping a former student of mine to make this really interesting project in Python, which was all about recognizing letters in the Russian sign language. And during the process of helping her, I kind of got to dive into the topic a little bit myself, and I thought it was pretty interesting, and I thought that, I might as well share it with you guys. And so in this video we'll dive into how we'll use this really cool repo that I found, and we'll talk about the authors and the folks who built that, and we'll use it to train a system to recognize our own hand gestures, and they can be anything, right? So it can be peace sign, thumbs up, thumbs down. Hopefully not only thumbs up if we're talking about this video. Well, hopefully, but yeah, I mean it's gonna be pretty interesting, and above all, I would say it's gonna be a really beginner friendly video. So if you have a project for, I don't know, for college or whatnot, and you're, or it's just a personal thing, you're learning more, I'll keep it very beginner friendly, and as long as you have basic knowledge of Python, basic knowledge of how to install modules and do things like that, I think it'll be good. And yeah, so now let's talk about the structure of what's going to be in the video. So the first thing we'll talk about is kind of the top level overview of in my opinion, two main approaches that you can take when performing hand gesture recognition: the pixels first approach and the landmarks first approach. We'll do that in a very fancy Google prezo that I've put together in 10 minutes, but it's gonna be good. We'll kind of cover all the main ideas that you need to know, so that when we jump into code, if you're that you have a way of understanding why things are organized there the way that they are. Then once we have that sort of top level understanding of the different approaches there are and stuff like that, I'll show you a really cool repo that I found in its English translation that makes it really easy for us to get started with hand gesture recognition and training something training a neural net on custom hand gestures. And that repo uses Google's Mediapipe framework, and that's a framework that you people install in Python, and it has all sorts of really nice things that make it really easy to get started with this type of computer vision tasks. And then on top of Google's Mediapipe, there's a really simple Keras neural network that takes hand landmarks and classifies them into their actual gestures, which we'll cover all of that. And then we'll look at the code and how we can use the repo to train something on our custom gestures, but I'll also walk you through at least the interesting parts in the code that it might be useful for you to know if you want to take this thing and modify it and build it into some of your own projects, or maybe build something completely new. It might be useful to kind of know where some of the main magic is happening, so to speak. So if you're excited, smash that like button, consider subscribing to the channel if you like it, and as always, if you have any questions throughout the video, comments, whatnot, just leave them in the comment section down below, and let's get started. Hi again everybody, it's Ivan from the future, actually, and I wanted to tell you two things. And the first thing is that it's gonna be a slightly longer video than usual, but I really enjoyed the in-depth kind of coding explanations and the training explanations we dove to, so hope you'll enjoy it. But if you want to skip to any specific part of the video, I'll leave the timestamp, so feel free to jump around. I always find that useful, so hopefully you'll find it useful too. And second is that this little fragment where I explain the top level of how everything works and get recorded properly, so I'll just quickly re-record it and then proceed normally with the video. So now let's talk about the top level understanding of how things work in the repository, and how we can approach building such a system that grabs the frames from the camera and recognizes the hand gestures in those frames. So the first kind of part that needs to be handled is the actual part of grabbing frames. In my case, it's from the webcam, and grabbing them in a way that we can interact with them and work with them in Python. And that's handled in the repository by really powerful, really cool, I enjoy working with it a lot, library called OpenCV, or Open Computer Vision, which is also kind of good news that it's using that, because it's gonna be pretty easy for you to build it into your own projects, because it's such a widespread such a massive library used in so many places. Really powerful, really cool. And in this video, we'll talk about like the examples of building such system to recognize certain hand gestures, like like the peace sign or the the OK sign, the thumbs up sign. I don't know why I just did that, but I know why. Or like the rock and roll sign or something, right? Which I wanted to say is just like if any of these gestures like don't mean to you exactly what they mean to me in some part of the world, because like I know they can mean different things around the world. Yeah, it would be funny. Just let me know. Pretty sure it shouldn't be anything too crazy, but yeah, like, let me know if some of the gestures that I'm showing, like if they mean something different to you. I think it would be like a nice educational thing, I guess. So cool. Now that we talked about like kind of this first part of the system that's grabbing frames, uses OpenCV for that. How do we actually build like the main kind of crucial system that's capable of taking some of these frames and actually like all the drawings, like all this like little pointy like dots here, like labels, that's OpenCV stuff. But how do we actually handle the system that's recognizing the hand gestures, right? So the first kind of hint that we can take at how we can approach solving this problem is by thinking like, we had frames with hands, right? Like hands can be all sorts of different shapes, gestures can be all sorts of like different shapes and different, people can have different hands that are doing different hand gestures with different slight variations and different slight, specifics. Backgrounds can be different, lighting can be different. Like all of this is kind of hinting that it would be really, really difficult, if not impossible, for a human being to write like a comprehensive system, like just purely algorithmically with code that would be able to tell us exactly which hand gesture it is, right? So this being like such a broad task with like different ways that the gestures can be presented, different backgrounds, all that stuff, it's kind of hinting that we should use a machine learning approach, or as we'll soon talk about, like a deep learning approach, like in specific. So the first machine learning, or as we've talked about more accurately, like deep learning, because it uses like deep neural networks approach, is something I would call pixels first approach. And that's because we're grabbing we were taking the RGB matrices, which RGB matrices, like it's essentially, all of the frames, all of the like images are represented in computers as matrices. At least it's a very like well-known format of like an RGB matrix. And we pretty much can get that with OpenCV by like grabbing frames from the webcam. So we get like this RGB matrix, which, contains pretty much all of the information that's in the image. We pass that through a convolutional neural network, which is a special type of a neural network that's optimized to work specifically well for images, and we get some sort of classification. So that would be like the pixels first approach. Okay, and that's the part where I hand it over to the Ivan from the past to continue with the video. And so that's approach number one. The second approach is it's a little bit more multi-layered, but it starts off very similarly. We grab the frames from the camera and pass them through a kind of neural network, but this neural network is different. This one is not supposed to give us the definitive like answers to what gesture the hand in the frame is showing, but it's supposed to extract hand landmarks, like this kind of pointy skeleton-looking thingies of the hand. And then we take those landmarks and we pass them through another much smaller and much simpler neural network architecture, like a feed-forward architecture, and that one gives us like the final classification, like what sign the hand is showing. So the main like drawback, the main like disadvantage of this approach would be that like training a neural network to like extract these embeddings is like much harder of a task. But we actually don't have to train it, since like it's a pretty well-known problem, and there's they're like pre-made like ready neural nets that we can use for this task, and that's where like Google's Mediapipe is gonna come into play in just a few moments. And so like if the whole like we don't have to train this thing is not a problem, right? Then we can actually start looking at the like advantages of this approach. And the main advantage is that we have this like really cool, really reliable neural net that's capable of like extracting hand landmarks. Like training a neural network on like hand landmarks to recognize gestures is a vastly simpler task than training it on pixels. Because, as I was saying, hands can be different shape, they can have different finger lengths, they can have like, I don't know, different skin color, different, I don't know, like just really, they can be really different. And lighting can be different, and the cameras can be very different. And so for us to train like this simple system, we'd need to collect a lot of training data. Like we'd need hands that are on this type of like fancy flowery background that I have, but also hands that are like on, I don't know, like a blank like white wall background, or on the like brick wall background, or on just like the countryside forest background, if you want the system to be really reliable like that, right? But with hand landmarks, kind of all the like heavy lifting ends up being done by this like kind of neural net that's extracting this like landmarks. And once it's extracted the landmarks, it's pretty much all of the data that the smaller neural network needs in order to do like a classification. So we leverage this like really powerful pre-trained neural net that's extracting these embeddings to be able to train a much smaller neural network that's much lighter, much easier to train, and that requires a lot less training images. So for instance, if you want to train it to recognize a peace sign, instead of me going and like collecting, you know, peace signs in all sorts of like different, you know, backgrounds, I can just show like the peace signs, maybe in different like couple different orientations and in a couple different like, I don't know, ways that you can show it or whatnot, like and that'll be enough. And like that's the power of this approach, that we're leveraging this like cool pre-trained neural net to extract the landmarks, so that we can train a much smaller, much simpler neural network to perform the actual classification. So now that we've talked about this like landmarks first approach, you might notice that one step here is missing, and that step is that like the neural network which extracting this hand landmarks, and subsequently the neural net that's classifying the hand gestures, it doesn't really need to look at all of the frame. Like it doesn't really need to look at every single pixel in the frame to recognize a hand gesture. As you may guess, it really only needs to look at the actual hand, which means that like all of the like background and all of the like, I don't know, like the other part of my hand, or the other, I don't know, like me, the background, all stuff like that is like, it's not important. And so we can make the whole system a lot more reliable by first cropping the hand, like the area in the image where all of the data that we need to make the prediction as to what hand gesture that area is showing is contained, which looks something like this. We grab the frames from the camera, starts off the same, but then we pass those frames from the camera through a hand detection model, which, you know, pretty much detects the hand in the image and like crops it. And then we take that cropped hand image and we pass that through that like powerful neural net that gives us the hand landmarks. And then those hand landmarks we pass through a feed-forward neural network that performs the classification. So that's actually like, I would say, you know, if not the most effective, then like in the context of what we're talking about, like it's definitely the most like effective, efficient way of recognizing hand gestures on a single hand. Now, looking at this approach, it might look a little bit complicated and as if it would be difficult to implement, but like I actually kind of assured you that it's going to be really easy to implement for one main reason, and that is that a lot of the work has been done for us. So for example, this stage with hand detection and landmark extraction is like handled really well by Google's Mediapipe framework. And so, as I'll show you like in a couple moments, we pretty much just like run some Python code and it's detecting the landmarks. And that second stage, which has to do with the training of like a smaller feed-forward neural network and like collecting training images and all that stuff, is handled really well by the repo, which I'll show you in also a couple moments. So in reality, it's like super easy to get started, but always when working with these types of approaches, I find that like it's always useful to like have a top level understanding of what the different pieces are doing. In that way, you just, you know, it's much easier to then apply it to your own problems, or to then maybe improve on it, or just like debug it if something goes wrong, you know. So that's like the top level overview of how things work here. And so right now we're on the website of the Google's like Mediapipe framework that's used in the repo that I keep telling you about, show you in a couple moments. I keep telling you that also probably, right? But yeah, we're right now on this like on its page where it kind of explains what's it doing. And here we can see like the models that are used is the palm detection model as we've talked about here that detects the palms. And the next model is the hand landmark detection model, which takes the cropped palms, like cropped like hand images, and performs precise key point localization of 21 3D hand knuckle coordinates inside the detected hand regions via regression that is direct coordinate prediction. So all that is said that it classifies the landmarks. And here they provide, fancy way to say that. And here they provide like the Python API for us to try it out. And so all you need to run this thing is to have OpenCV installed, which is like really easy to do, like just like through pip and stuff, and then install Mediapipe. It'll probably run like some TensorFlow light neural nets in the background, but all of the running is done on the CPU, and it's like, it runs pretty quickly in my case, like I'll show you in a moment. I have like two webcams, like this one, it's the my kind of laptop's like inbuilt webcam right here, and as you can see, like I run it and it's running like pretty fast, all done on CPU, and it's detecting the hand landmarks, and it's pretty cool how well it works, right? Like, my hands can be like in all sorts of different like orientations. They can even like obscure each other to a certain extent. It'll still be working. I can kind of like even hide my hand behind the mic, and it's still able to get the whole picture. And like for all the like gestures that like if your gestures are like operating like on some sort of like closed palm way, like as you can see, it's also handling like that quite well as well. So like that's pretty much like the simplest way that we can work with Google's Mediapipe framework and kind of get it to show us some results. If it's giving you like any errors here, like Mediapipe's not installed or like CV2 not installed, just like go and install like OpenCV and Mediapipe. Like that's pretty easy to do, honestly. For OpenCV, it's like pip install in the Python console, pip install OpenCV-Python. For Mediapipe, it's just pip install Mediapipe. Just in case any of you have any problems here. So that's us testing kind of like the basic Mediapipe hand landmark detection application right here. So now that we have looked at the Mediapipe part of the pipeline of our hand gesture recognition system, and pretty much covered like the extraction of frames, palm detection, and hand landmark detections using Mediapipe, we'll fill in the remaining kind of steps that are required to recognize custom hand gestures, which is like collection of data and then training like a smaller neural net to perform that task using a really, really cool repo. And let's take a look at it. So it's this repo that's called hand gesture recognition using Mediapipe by Kazuhiro Takashi. So it's a really awesome repo. And the one we're going to be using is not this one though. It's this one, which is just a English translation of the original repo. So it's like a fork of that original repo translated into English. And so the original repo is by Kazuhiro Takashi, and the translation is by Nikita Kiselyov. Right here is the author of like this translated repo. So now in order to get this repo, you can either git clone it using this URL, or just go here and download the zip file and just extract it somewhere. I've put it on my desktop right here, and I have it opened in an IDE called PyCharm, which is just essentially like a place where you can like write Python in a nice way, but you can use like any IDE that you like. I'm keeping it like beginner friendly, but like it obviously you can use the whatever way that you like to write Python. I prefer PyCharm for these types of things. So now that we've git cloned this repo, it actually shouldn't have this file because we just created that. I've just created that a couple of seconds ago to test Mediapipe. So now we can go ahead and launch the app.py file, which pretty much launches which is pretty much like the main file in this repository that performs inference in the frames from our webcam and processes them in a way where it detects hand gestures. So now we can see that right out of the bag, it's able to detect a single hand. I'll show you how to like enable like multi-hand detection in a few minutes probably, but it's able to detect a single hand, and it has that like hand gesture recognition built in. In this case, it recognizes the open palm, like closed palm, and OK sign, and the pointer. So there's also a part in this repo that deals with like recognition of like this point history, drawings. That's not what this video is focused on, but like feel free to explore it also. We're focused on this primarily cool part where we, recognizing like hand gestures, like this is closed hand gesture, and this is like open hand gesture, OK hand gesture, and how we can like add some of the like custom hand gestures. So yeah. So now let's start looking at the code and maybe like tweaking a few things here and there. So like the first thing is we've noticed is that it's only working right now on detecting like hand gestures in one hand. You may want to use it to detect hand gestures maybe on 2 hands or on 3 hands or on, I don't know how many hands you want to put into work here, but so now if we look at the Mediapipe docs right here, we can see that there are several supported configurations options, and one of them is max num hands, which is defined in the Python code here. And so in our case, if we find it in our code by searching max num hands, it's set to 1. We can set it to 2, and it will be able to detect 2 hands pretty much. Yep. So now if we look at at the screen right here, at the this OpenCV window, which is like handling like all of the like displaying of the drawing, as I was saying, you can see that like the detection is happening on 2 hands. Here's something interesting that I didn't notice like at first, but then I was like, there's got to be more to it, right? If it's doing that. So as you can see, it's detecting for instance, here I have my right hand, right? So if I flip it around, it's still the right hand. If I put it like on the other side of the screen, it's still the right hand. And if I flip it around like this, it's still the right hand. So same thing with the left hand. So it's like you can't really fool it. Like however I want to like rearrange my hands, it'll know that like this one's the right hand, which it is, and this one's like the left hand, even if they're like completely swapped on the like complete like opposite sides of the screen pretty much. So that tells us that Mediapipe also has like an inbuilt way to detect the handedness of a hand, like whether it's the right hand or whether that's the left hand. When can that be useful? So for instance, in the like example of like the former student of mine that I was talking about in the beginning of the video, where she was training like a system to recognize Russian sign language letters that you can do like with one hand. She used like this feature of Mediapipe, which allows for like for the handedness detection to essentially have always one hand be the one that's like inputting the digits, right? To be like that's doing something that's like from which we can read the gestures, and the other hand be the hand that's like controlling the inputting and the typing and all the other things. So like you can use this functionality to like separate maybe from this hand you're detecting the gestures, from this hand you're detecting like different gestures, and that's performing different actions in whatever the application that you're working on. One thing to notice here, you can see that like whenever I put like, so for instance right now it's running at like 17, 18, 16 FPS, something like that. And that's because what happens right now when there are like none of my hands detected is that like all it's doing is that it's running the palm detection, the hand detection model that like detects palms and like grabs them and stuff on the frames. But if I put in a hand, it starts to also run the like hand gesture recognition models and the landmark detection. That's like taking more of the processing power, and as the frames per second slow down, if I add another hand, and thus there's like a little bit more processing happening also on that front. So pretty much the only limitation for like running it on like a lot of hands is that like it might slow down the application, but as you can see, it's like pretty remarkable. Running on CPU, running pretty fast, kind of doing what it pretty much needs to be doing. Yeah, And so here in the docs, in the like output section, it also talks about multi-handedness. I think that I wanted to note here is that like when it's determining the handedness of a hand, it's assuming that it's taken with like a front-facing or like selfie camera, as it says here. And if it's not the case, then you can like swap the handedness in the application. Just something that I wanted to note here. And by the way, here in the docs, they also say like how the hand landmark detection model was trained, and they say that it was like trained on like manually annotated like these types of images of people's hands, and also on some of the like high quality synthetic hand models over various backgrounds, which also was fed into like the training data. So now let me actually start giving you kind of like a walkthrough over like the main points in the code so that you have that understanding. So first of all, so the main kind of action in terms of like performing this type of inference in the frames from the camera is happening inside the main function. And here again, we'll focus like on the kind of OpenCV structures that fit in the frames, and then there's preprocessing that's performed on those frames. But pretty much to anybody who's worked with OpenCV, that's going to be quite familiar. And if you haven't worked, you're going to have like a series of cool videos about it if you're interested. So we're defining like the camera capture and stuff like that, which is like essentially the webcam that we'll be using from which webcam to like grab the frames into the Python code, stuff like that. Then this structure with the like while loop. What am I doing? The structure with the while loop and the wait key inside of it is something that's probably like everybody who's worked with OpenCV will recognize. It's essentially a way of creating this like while loop, because like we're grabbing frames from the camera constantly, so it's like a while cycle where we're, you know, grabbing. But for this type of loop to like work with OpenCV, there's gotta be like a wait key command present there, because like it has to wait for it to also input something into the window. I can kind of show, like if we remove this line here, first of all, like it'll crash. But if I say like, you know, something like that, if it doesn't have the wait key, the window will just be like blank, because it, you know, yeah, as you can see, like it's completely like not working, because without a wait key, like OpenCV is just, I don't know, the wait key kind of adds the delay to the while loop, so that like, because there is a natural delay between the frames from the camera, you know, it's not shooting in like a billion FPS, and it's also adding like that ability to like wait for user input there. But anyway, it's not so much an OpenCV tutorial. I'm just pointing out that like very general structure used in a lot of places, like very flexible in terms of how this thing's put together is what I'm trying to say. Then we scroll back here. We use here camera capture that read, which grabs frames, and so like this first element is like it's either true or false. It's false if there aren't any frames. Since we're in the webcam, it's always true, because like there are always new frames. The image gets flipped and then converted from BGR to RGB, because OpenCV has its thing where it kind of prefers to have everything in BGR from the get-go, but we can kind of convert it using this thing. Then the interesting stuff happens. So this hands thing has actually been defined above, and this hands thing is defined using MP. MP is like a shortcut in this case for Mediapipe, and so the hands variable here is essentially like a configured with like this hyperparameters Mediapipe application that's tracking hands. And here in this like OpenCV code, we're grabbing frames, converting them to RGB, and then we just pretty much like passing our image through hands.process, and that in its turn returns us the hand landmarks. I've added here a handful of like cool prints, and what I want to do is like, it may get a little bit convoluted at this point, but like I want you to kind of bear with me, because it's pretty cool, I think. So we're actually gonna go and start printing the landmarks. Like this first print is gonna show us kind of how we first like are getting them from the Mediapipe. As you can see, it's like a bunch of these points that have x and y and z coordinates, which is pretty cool. But that's not what we're ultimately going to be using. We're not going to need like a third coordinate for a point. We're kind of going to stick to that two-dimensional life, I suppose. So let's jump into the next print, and this one is a print after the hand landmarks get converted into a list, like a two-dimensional list. And this one's gonna be a tiny bit more interesting. Let's check it out, because like it's gonna be like closer to what we'll end up using. So now that's what I'm talking about. So after that conversion, we can see two main differences. So first of all, like as you can see, there are just like two coordinates, x and y, pretty much per point, which is also what's used to like draw them on screen. And the values here are actual like pixel values. So now let me show you kind of something cool. So this first point here, according to the Mediapipe docs, is like it's the wrist point. So like it's like this point right here, and we can kind of see that, like for example, if I take my wrist and the closer my wrist moves to like the left top corner, which is where like in OpenCV pixel life, like here it's like 0 0 coordinates, like 0x 0y, 0 width 0 height. In other words, here it's like full width full height pretty much. So as we're getting like, let me actually do some, let's just print like the first element, like this first kind of wrist point right here, so that like there isn't a billion of those on screen at the same time, which I get it, it's like it's confusing. So let's do that. So now I'm just printing like this like 0th element on that like process list, which is like the wrist point. So as you can see, like the closer it gets kind of to the left up corner, like the lower the values are. I'm just trying to get it like as close there as I can without losing it. And like as closer it gets like to this place, the larger the values get in general. And if I move it here, then the x values get really, really small, while the while the y values, like the height values, like the y values, pretty much they stay in the same. And on the other hand, if I move it somewhere like here, the y values are really, really low. As you can see, it's like 100, 115, 800, 120, stuff like that in terms of the y values, and the x values in this case are like 700. So like you can see kind of how, using the example of this one point, how they're represented at this point in the like processing pipeline as like the absolute like pixel values. There are a few more steps coming in terms of like preprocessing them, but it had it's like a cool intuition to know that like these things aren't just like printed dots, they're like actual values that we can understand where they come from, you know? Now the next part is really, really cool, but behind the scenes I was kind of bashing my head for the last like 30 minutes because I was thinking like, how do I best explain it? Because like it's really cool to understand. It's really crucial to like understanding how that like final part with the feed-forward neural net is gonna work, but it's like it's a little bit convoluted. But I'll do my best, and you just please bear with me, okay? So like the whole concept of a benefit of using like this like landmarks approach for fitting that into like that feed-forward neural network, you know, in the last step pretty much for classification, is that we don't have to worry about the position of the hand, like where it is, and we don't have to worry about like the, I don't know, the individual like shape or color or whatever of a given hand or like the background, you know. But with that, we need to find a good way to pre-process these landmarks to be fed into a feed-forward neural network. And pre-processing is like it's like a very crucial concept that pretty much thinking about how to like properly pre-process a data set for training a neural net is like, it's like half the battle many times, honestly, because really so right now we have a problem, as we have seen, with these values being defined as like absolute pixel values. Like for instance, I don't know, right now my the value of like this like wrist point, right, like on my wrist, like this 0th point, the value of this guy right here is like close to like, I don't know, maybe it's like 50x, 50y in pixel coordinates, right? But if I move my hand here, right now it's gonna be like, I don't know, 400x and 300y or something, right? So Same applies to like all of this like other 24 points on the hand. So what's the problem here? Well, the problem is that like if we feed that to a neural network somehow, this is like a vastly different hand in terms of values than this hand. Like if we just like focus on this point, like this wrist point and this wrist point, like say like these 2 points, right? Like this guy and this guy, they're pretty much on the same distance relative to each other here as they're here, but like their values will be vastly different because right now the representation of hand landmarks that we have is like, you know, this like list that we've processed. Well, not we, the author of the repo, but you know what I'm saying, is heavily relied on like the actual pixel values. Now, it's not just relied on them for the sake of being relied on them. It's relied on them because like there's a next step coming up, and that next step will pretty much address this very problem. So to address it, we need like some sort of system where these landmarks, when they're going to be fed into a neural network, and they're going to be fed, by the way, as a vector, as a vector which is like a one-dimensional list of numbers, which will look something like this, like 0.5 minus 3, 0.4, no, 0.4 minus 0.4, 0.1. You get the point, where they're going to be like pairs of x coordinates and y coordinates, kind of as we've seen with the wrist point. And so we gotta somehow find a way to like convert this like absolute pixel values in terms of the frame into like some relative values, where this hand here and this hand here will have roughly the same values, you know. And that's done through a process called, you know, normalization, where we're gonna like normalize these values between the ranges of -1 and 1. And in this way, and I'll have like the whole like little painting prepped here for that I will dive in a second. But for now, like basically, you know, we'll follow the algorithms. We'll dive into what they're doing and what are the actual like ways that we can like normalize this whole thing, so that it's like relative to each other. Like this hand, which isn't just gonna solve the problem of hand being in all sorts of different places, like it's also gonna help with like, you know, if my hand is a little bit farther away or if it's like a little closer, as you can see like the distances kind of change. But like if we normalize it to like the relative coordinates, like this thing will be roughly the same as this thing. So like all the like scale problems will also be like handled in this way. So now let's dive into like the actually like what's going on in this like preprocessing algorithm in this case, you know. So next up in the code, this like the list that we've talked about of like, you know, absolute pixel values like in the frame gets passed through a preprocess landmark function that's doing like all the like conversions. And upon the like output from that function, we can see how those values change from being like absolute pixel values to being let's give it a couple of seconds to load, but to being like this floating point numbers with the values not surpassing, you know, -1 or 1, in a way that they're being like normalized in this way. But like it would be really cool for us to understand what's actually going on behind an algorithm, because before doing this video I kind of had like an idea of what I was doing, but like when I actually started, like I kind of had like my idea of like how would I do such thing. But the thing that like the author of the repository did, you know, like it obviously does the job, and I think it's pretty cool, and it's not something that I would have thought immediately off the top of my head. So I think it's like worth taking a dive into it. So first thing that happens here is that we create this like temporary landmark list copy, which is essentially like that, you know, list of, but remember like this like pair values of like pixel values that look something like this, you know, where like x and y, and there's like 20, 24, right? Oh no, 20, sorry, there's 20 of them, yeah, of this like pairs of hand landmarks. And so the first thing we do here is like we convert this whole list to relative coordinates. Now, what does that mean, relative coordinates? I kind of have like a little not fancy at all, I get it, thing that I drew like in Paint. But for example, let's imagine that this is our wrist point, right? This is our like point with the index 0, right? So in this case, the process of converting everything to relative coordinates is done through taking the point with the index 0, aka like this wrist point, and subtracting that base point from all of the other points. And this is kind of what I'm doing here, for example. Like this is our base point, like a wrist point, and it's the base point because again it has the index 0, because again it has the index 0 right here. We subtract from it, and we subtract from every point, we subtract like this kind of like base point, and if we subtract like base point from itself, we get 0, 0, and so yeah, like base point minus base point is like 0, 0. Let's say for instance we're looking like at this point right here, right? Let's say it has coordinates like 400 to 50, like it's a little bit to the left and a little bit higher than like this guy, right? And remember like this is like 0, 0, and here it's like max in terms of like x and y coordinates. So for this point it'll be like 400 minus 600, it'll be like minus 200, and 250 minus 300 will be like minus 50. So in this way, by performing this operation for each of the points here, we get kind of like relative, kind of like each points become represented as of their distance to the wrist points. Like, you know, this point's like this far, you know, this distance, etc., etc. Like each point gets like represented as itself minus the base point, and thus we're get represented as like how far away it is from the base point, actually. You know what I mean? Then there's, so like that's pretty much what happens like here. Then that happens for like every point in the list, and it gets converted to a one-dimensional list because the input to the feed-forward neural network, it's gonna be like a vector, a one-dimensional list pretty much. And here's another really interesting thing happens. We get we get this like relative values here, but they're still like minus 200 and minus 50, or like minus 100 and minus 250. They're dependent on like where the hand is in the frame, pretty much. You know what I mean? So like they're not relative. They're you know, if a hand would be like, you know, if this hand were to be moved slightly to the right, all of these values get pushed. Like, let's say this thing would be like 700, like this whole thing would be also pushed by like 100 pixels. You know what I mean? So like we gotta normalize them between like this like more floating points, like values between -1 and 1 pretty much in this case. So the way that it's done by the author of the repo is we take the maximum value. So we end up with this like list that's still like expressed in like pixel values relative to how far away from this like wrist point. Let me look at a different color. Let's pretend like I'm drawing something fancy in Paint. You know what I mean? Yeah, it's like we get like a list that's filled up now with like this value. So like 0, 0, minus 200, minus 50, minus 150, minus 250. But it's still like pixel values, you know? They're not like relative, you know, normalized floating point values, you know? And we get the floating point values by taking this list of like relative values and finding a maximum value on it. So what this expression here does is like ABS map ABS template landmarks list. It's essentially like disregarding all the like whether a number is negative or positive. It's just getting like absolute distance. So for instance, we have like a list that looks like this, like -1, 2, 3, like this part here would convert it into like 1, 2, 3 pretty much. It's useful in our case because what we're doing here is that like we're taking all of these values here and we're converting them into like this like absolute length distance list, you know what I mean? And then we're finding like the maximum element here. And spoiler alert, then all of them get divided by the value of the maximum element. And so you may kind of ask now, like, how does that look in this like actual drawing? So the point that's like farthest away from the wrist point here, from like the 0th point, is, I mean, I kind of eyeballed it here, but like I'm assuming that it's like this guy here, and I'm assuming that it has values for 50x and 50y. y, such that when we perform this like subtraction where we take 450 minus the base 600 in this case is like minus 150, and 50 minus 300 like minus 250. It's like this is like our distances pixel values list, right? And we perform that for every single one of them. And like minus 250, when it gets converted to like this absolute length, will be just 250, and it'll end up being, in this example, the maximum value. I have it written here, kind of like maximum value like 250. Like we've identified it in like this line of code. So then what we go ahead and do is very simple. We just go and we divide every single value of this like distance pixel values. We divide each of them by the maximum value, and we end up with something like this. Like this thing will be like minus 150 divided by 250 will be minus 0.6, and minus 250 divided by minus 250 will be just minus 1, aka like the kind of farthest point away from like our kind of like base point relative to which everything is happening here. Then for this guy it'll be like minus 200 divided by 250 will be minus 0.8, and for this guy it will be minus 0.2, and for the base point, as you may have guessed, like it'll still be 0, because like 0 divided by 250 is still 0, stuff like that. So that's pretty much what we're ending up with here, and that's pretty much what this function returns to. So that's pretty much what this function returns to the preprocessed landmarks list, And so to put into like simpler words, the intuition here of the preprocessed landmarks list is that it's normalized values between -1 and 1 that are determined by how far away they are from the base point, which is in our case like this like wrist point, It's like normalized values between -1 and 1 with the values determined by how far away they are from the base point, pretty much. It's like pretty cool, but it's pretty cool that we've like gotten that, but then we've also like walked through the code, like we see the code, we see like the intuitions. I really tried my best with this drawing, so that's why I'm excited for it, I guess. Hopefully it helped with the understanding, And so just like one last thing that I'll say about the drawing is that like in this case for the middle finger, the values are like they're like minus 0.6 and minus 1 here. If the hand was pointed in the other direction, then there would just be like 0.6 and just 1, because the value here would be it would be like a positive value now, because it would be like like I don't know 700 minus 300 or something. So if it would be flipped, it would be like 0.6 and 1. Just another cool observation. Okay, cool. Now after we've like talked about all this, we're actually like this close. We pretty much know all we need to like start training and stuff like that, So one quick thing before we jump into training, just like actually really quick thing. So like as I was saying, this repo deals with like two things, which is hand gesture recognition, but also point history recognition. So for instance, when it identifies that you're showing like a pointer gesture, it started drawing the circles and like recognizing like I'm rotating counterclockwise or that I'm moving or whatever it is that it's like recognizing right now. This is like awesome. Maybe I'll make something like that in the future, but like that's kind of beyond the scope of this video. So I just wanted to like really quickly show you how you can disable it. So the way it works, as I was saying, is that like when the hand gesture recognizer identifies it as the pointer sign, it invokes like all of this like point history functionality. We can go into the labels file, which we'll talk about in more detail very soon, and see that the 0, 1, 2, that the pointer index has like the pointer the label pointer has the index of 2, which means that like in the neural net it also has the second index. And with that we can go here and check. Yeah, it seems correct that like whenever our key point classifier gives us the hand ID and it equals to 2, it invokes this like point history stuff. So like the little not super fancy, but like reliable way to disable is to just change it from like if hand sign ID equals from 2 to like something like not applicable or something like that. Obviously a hand sign ID, which is like a number, will never be not a string not applicable. So thus it'll never really invoke this like point history thing unless you want it in the future. In this case, you can like bring it back, and so as you can see, like it's like disabled now, nothing in terms of like point history and stuff like that. But in the future, you want to like work with it. You can like maybe train like a custom gesture, and I don't know, like put in the index of that here. And if you also don't want the like finger gesture writing right here to be displayed, you can just like go into the draw info text function and just like comment this little guy out. I did it by pressing like Control and slash in PyCharm to do that, but it's not super annoying. But like maybe if you're building like a specific application, you really don't want to include that stuff. So there it is, gone. Now on to training, for real this time, for real. So now let's finally talk about training and how we can train the model and within like this pipeline of systems to recognize our own like custom hand gestures. In the repo, we can see that there are instructions that we'll be following to perform the training successfully, but I suggest that we talk about training in the context of three main things, which is preparing a data set, training a model, and then testing. So let's dive into it. So first kind of interesting thing to understand here is like how the author of the repo handles the dataset collection and like just in general storing of the dataset. So for the key point, we're interested here in key point classification in particular. Same thing as like hand landmarks classification. On top of that, like kind of the thing is we train on top of hand landmarks pretty much. So the training data is stored as a .csv file right here, and I'm opening here like inside a folder so that like in case you're not using PyCharm and you don't have like the same layout, that you also know like where to kind of find those files. But I can actually open and view them in PyCharm like this, and here you can see the keypoint.csv file, which contains like the training data that, at this point it's what the author has collected. That's kind of what the repo comes along with, and the labels. So here we can learn that the first column here is a class index. So for instance, the classes of these things are like 3, here's like 2, the class index, here's like 1, here's like 0, and etc, etc, etc. Here it's just like 4 classes that it comes along with, but we'll start creating them in just a few moments. The thing about classes is that they're matched by a label file, where for example the class with the index 0, so they go like 0, 1, 2, 3. So pretty much all of these guys here are with like the 0 as the first column are the landmarks for the class named open. It's like open palm in this case. And all of them, for instance, with the index 3 here are the landmarks for the class class OK, pretty much. So as you can see here, like the author says, like pretty much first column press numbers is like used as a class ID, and second and subsequent columns are key point coordinates. Now, how do we actually collect kind of like new training data in this way? So that's a great question. Let's dive into that too. So let's first, as an example, say that I want to keep this 4 classes. I just want to add like one new class to them. So for instance, I want to add the peace sign. So I'll say here peace sign in the labels file. And right now when I launch this thing, like obviously we haven't done any training, haven't collected any data. So like there isn't gonna be a peace sign, So it's like, but it's also not gonna give us an error because like it's just simply never gonna guess the class index 4, which should be the peace sign, but it's just the neural network never gonna go there because it wasn't trained on that data. But we can actually start training it and start collecting a few samples of what the peace sign looks like. Let's check it out here. It says that we press K to enter the mode to save key points, which means that like we press K inside the OpenCV window. So I can click here. My keyboard is like in the English language, and I press K, and it says mode login key point. So now, when we're in this mode login key point, we can press from 0 to 9, and it'll kind of add the classes with this index of the number that we press will be added to this like data set that we have here. I'll show you right now. So, for example, I'll go and I'll say peace sign, and it's gonna be a class with the index 4. And what I'm doing right now is like I'll literally start clicking the key 4 on my keyboard and be like 4, 4, 4, 4, 4. And as I'm clicking it, it's taking like a snapshot of the image, and like it's like saving this, this key points under the label 4. So I've clicked it a few times. I can go here, key point.csv. As you can see here, a few new classes appeared with the index 4 now. I wanna add like more, like that's, I think, we probably wanna get, like, you wanna get way less than you would have to get where you're just like doing the pixels first approach, but you still wanna get like maybe, I don't know, like 20 or 30 or something like that. So I'll go and be like 4, 4, 4, 4, 4. Maybe I'll still try kind of bit of them like different scales, even though it's not again as sensitive to that because we've like normalized that stuff. It's still I think useful. Some like rotations and stuff can be useful too. And then I'll go and I'll do them on a different hand. 4, 4, 4, 4, 4. Again, the cool thing here is that like the background doesn't matter. The any like specifics of what fingers are doesn't matter, like, so like if you train this thing to like recognize a peace sign on your hand, chances are like on somebody else's hand with this like landmarks, it's also going to be recognized. But yeah, let's say we've collected, let me update this guy. So, it's not a lot, but it might do the job. Let me add in a few more. Just maybe I wanna squish my fingers. Like if you know that like scales isn't the biggest deal here because it's really, maybe I wanna like try some of them, like like a little more, kind of squished fingers, peace signs or something like that. Maybe like these fingers can be a bit differently orientated, like this. Like depends on how much I wanna like go with it really. But yeah, let's say I've collected enough data. I'll press escape to like exit this window. Now the training that was like the first step. The second step, it's gonna be really easy thanks again to the author of the repo. The training is gonna be like, so like we'll be able to do it like literally without even thinking about it, but we'll still kind of look at the code. So for training, there is this Jupyter notebook for training on key point classification that we can run, and if we run like all cells in the Jupyter notebook, that'll pretty much do the training for us. Yeah, so what I'll do is I'll open the console in this folder and I'll say Jupyter notebook. Jupyter in this case like is a Python module that I've installed, which you can pip install Jupyter and you'll be able to open it too. And here I'll open the key point classification that IPyNB, pretty much the Jupyter notebook. So a few things that we want to note here is that essentially the what this thing is doing is that it's loading the data from the .csv file, and it's defining a model, which is like, so as you can see, it's a very simple like Keras neural network architecture here with this many like with like 21 times 2 input neurons, which is gonna be like a vector of values for like this like landmarks pretty much that are pre-processed here, followed by some dropout, 20 dense neurons, some more dropout, some more dense neurons. A very simple architecture, and with the output layer having the softmax activation function, because a hand gesture can be both like a peace sign and a K sign at the same time, which is what this guy is useful for. And the num classes is determined by like how many classes we have in our data set. In our case we'll have 4 by this point, or no, I think we'll have 5, right? It'll be like open, closed, pointer, and okay. And then it pretty much just like trains the model, saves it. The whole training happens like really quickly. So pretty much what you can do here is just like go and be like kernel restart and run all. No, just like run all cells. Okay, I see what it's saying. I forgot to modify this variable here, number of classes. As I was saying, now we have 5 classes, so it'll be 5. And now I go cell run all. So you can see it's training, and it's training like really quickly. It looks like, it says here that it's gonna train for 1000 epochs. In reality, it's gonna do like early stopping anytime soon, but as you can see, like the whole training process is like really quick in this case. And it's not gonna get much longer, honestly, because again, the whole neural network architecture here is like, 20 neurons followed by 10 neurons followed by, in our case, 5 neurons here. A really small architecture. But what's it's doing right now is it's learning to map like the input vector, and that input vector being the hand landmarks for all sorts of different classes to like its label class, right? So it's like learning to map this like relative landmarks to a number, to like an index, and that index represents according to like that index, like we make it so that it like corresponds to this like label file. You know what I mean? So now that it's finished training, it'll save the model automatically. It'll save it here with the model save path. And so pretty much, yeah, all you do is like, you say cell, run all the cells, it finishes running, then you can go and you can like click up, and if your label file is alright, and if like if everything went smoothly there, then you should be able to start recognizing a new hand gesture. So like, peace sign, there we have it. Peace sign. It thinks that this thing is a pointer, which when I see this, it's just a signal to me to like add more data, and I'll not think that anymore. Potentially it also like kind of looks a bit more reliable, I don't know, with this guy. But yeah, as you can see now, it's, we can have still the OK sign, the open palm sign, the close sign, the pointer, and the peace sign, right? And so now, yeah, pretty much these things, if it's like not working correctly, like in certain orientations, like when you train it, just like add more data. Just like do this thing again, like press K under the logging mode and be like, okay, like it's struggling on my left hand. Like this should be like a, this should be a peace sign, but it's saying it's a pointer. Let me press 4, so I'm like literally like pressing my keyboard again, like just like bashing it, like 4, 4, 4. As you can see, I could press like number 4, 4, 4, and then train with that data, and that should help, because like, you're feeding it more data. Last thing that I want to show you is we've handled now the example of like how adding one class looks like, right? Like modifying the labeling file, adding more data, running the whole training again. What if we want to like start completely from scratch and like get rid of all of these classes and just like do something completely new? Like let's say we want to have the, like thumbs up, thumbs down, and a rock and roll sign, like the horn sign, whatever it's called. I associate it with the rock and roll sign, so we'll just roll with that. So as you can see, training that model is like really quickly, and the main kind of bottleneck in this case is like the data. So in order to do that, like we actually, in this case, by the way, we haven't, like when we've added the new class, we haven't like kept an old model. We've completely retrained the model from scratch, just in a new dataset that like included the new examples. So to add like these new classes, we kind of have to do like low-key the same thing. So first thing I'll go and do is I'll go into that CSV file here, and I'll just delete everything here pretty much. So it'll be completely empty. Then I'll launch the training script again, and I'll collect some training data. So let's say we'll do like thumbs down. Hopefully this video is like a thumbs up, but like they're just for the playing around with it. Actually, I don't like thumbs down. I don't like the sound of that. Let's just do peace sign, thumbs up, and the rock and roll sign. Can we do that? Cool. So I say, okay, let this be like the peace sign, but never mind that it's already saying that I'm collecting like a new data set. So I'm keep pressing like 0, 0, 0, I enter the data collection mode with the press of the key button. Press 0, 0, 0, 0, 0, 0, 0, 0. Like literally like bashing my keyboard right now. Like, I don't know if you can hear it, but like pressing this key, each time I press the key, the data gets saved. Peace sign. Now let's do thumbs up. Like I'll start pressing 1. Now let's do the rock and roll like horn sign. I'll start pressing 2. And for more accuracy, you may want to add like the left-handed examples also. I've just added a couple wrong labels, as you can see. I have, but that's not a problem because I can just go and erase all of them because I did this thumbs up with an actual index. I did like this thumbs up with the index of 0, but that's for the peace sign. You know what I mean? So let's do some more like left-handed, like peace sign, 0, 0, 0, 0, 0, 0, 0. Left-handed, thumbs up. And the left-handed, like rock and roll sign. By the way, if any of these signs like mean something different, like in your part of the world, like let me know. Like I'd be curious to know what they mean to you, because like I kind of did some googling before that, and like I don't know, there's a lot of hand gesture info that this video does not need to be longer than it already is, I have a feeling. So okay, so I've collected the data. Okay, go and check out like our training file. As you can see, it didn't take me a lot of time at all. It just like takes some attention and stuff like that. I'll edit the labels file now for peace sign, thumbs up, rock and roll sign. And then we'll go into the Jupyter notebook here again and just press cell and run all cells again. Oh, no, actually just one thing we need to edit here is the number of classes. So like I'll go and I'll say kernel restart and run all. So yeah, just like don't forget to edit the number of classes. That's a good one for sure. Okay, so you can see it's starting training. we haven't collected a lot of data, so I'm assuming that it's gonna go by pretty quickly. Again, all the training I think is also happening on the CPU. Might be wrong, but like I'm pretty sure it is. Okay, so you did the early stopping and it saved the model, and after that's done, we can just go and launch the app. Again, like this file, because like the model file has been updated, so which is like this file right here. So now it should be able to do all the new detections. So like that's the peace sign, thumbs up sign, rock and roll sign. As you know, we don't have a thumbs down, so like even that's a rock and roll sign. Same thing on the left hand, peace sign, peace sign, rock and roll sign, rock and roll sign and thumbs up, rock and roll, peace sign and rock and roll sign, peace sign, rock and roll sign, thumbs up sign, peace sign. And then, like whenever you get like these edge cases and like any problems with like accuracy and stuff, you can just like go and again do this whole thing, or like, hey, like let's train it like this is like that's like, I don't know, like the peace sign, and just add more data that looks like this but with the index of the peace sign, and just run the training again. Yeah, pretty much the only thing that I'd mention here is that like you may just like use if you want to have like more classes than here for your hand gestures, you can just like write some Python conventions in the code to just be like, the number of the key pressed, say like +10 or something like that, open up the whole new array of numbers. But I don't think there's any like a limit to how many gestures you can have. As I was saying, the person whom I was helping did like that for the Russian sign language, and the Russian language is like 33 letters or something like that. So you can really do a lot with it, and yeah, as you can see, like it's like pretty cool. We're like rock and rolling and peace signing and thumbs up in here. I'm kind of like hinting at something here, guys, you know? I don't know what I'm hinting at, but I'm hinting at something. What can that be? I don't even know what I'm hinting at, but can you guess that? I'm not, just subtle, you know. You know. Okay, fine. But yeah, that's pretty much. So a few more things that are valuable to mention here is that, like, if you want to like incorporate this into like your own project, like, yeah, some ideas is that, you know, what the former student did is like she did like, you know, she focused, like, as I was saying, gesture recognition, like on one hand, for instance, on the right hand, and for the left hand, she like hard-coded some rules that, like, if you move your palm in a certain way, then it does like, or like if you move your finger in a certain way, then it does like the typing. So it's like showing the sign and like typing it and stuff like that. So like you can experiment with like hard-coding some of this like landmarks. And yeah, I hopefully that like this whole part where I explain like OpenCV and the code and stuff like that, the training process, is actually useful, because like as I was saying, pretty much with the knowledge of OpenCV that I have, like it wouldn't take me much of an effort to like build it into some of my own stuff, or like to build it up and build something cool. Again, massive shout out to the author of the repo, this person, and to the person who translated the repo, this guy. And yeah, just like pretty much, I hope you enjoyed this video. You know, smash the like button if you enjoyed it. Any comments, questions you have, drop them in the comment section down below. And consider subscribing to the channel if you enjoyed this. It was really fun for me to make. It was fun to think to do this stuff for me as well, and I hope that you got some value out of it and enjoyed this video. And I'll just say, you know, hope you're healthy, hope you're well, and you know, hope you enjoyed it, and I'll see you in the next one. I guess, you know, peace.